Hello and welcome back and very good morning to you all. Today we shall be discussing about the electric dipole when it is placed in a non-uniform electric field. Earlier we did a case of torque acting on the electric dipole, that was the uniform field. But today we have got a different topic, that is non-uniform field and the dipole is placed in it. Okay, so there will be two cases. Generally, we shall talk about the parallelism or anti-parallelism orientation of the dipole with the electric field, and then we shall see the behavior of the dipole. First case is, suppose we have a non-uniform electric field, and that is shown by this black arrow E, and the field is such that this is increasing in this direction, right? Increasing means field is, say this is 1 Newton per coulomb, this is 2 Newton per coulomb, 3, 4, 5, 6, and this way the field lines increases, or the strength of the electric field increases as we go along the x-axis. Now what if a electric dipole is placed over here? This is the combination of two charges and separated by a small distance 2a or whatever, and its dipole moment, as we know that it is along minus to the positive charge. So this is increasing electric field and this is the direction of the electric dipole. Now what happens? Obviously the field is increasing or non-uniform, means earlier we did the force on this charge will be F1. What will be the direction of that force is, that is this way. Now the force on this charge will be this way, but the forces will not be equal, rather they will be unequal, or different forces are acting on this dipole due to the non-uniform field. See how? If this is equal to 10 Newton, a force acting on this negative charge, the field being large at this position, the force on this charge F2 will be more than 10. I'll obviously say it is 15 Newton. Then what happens? The total system, entire system experience some net force in a particular direction, and that will be this direction. It means the net force will be acting along this direction F, and F will be equal to F2 minus F1, and that's equal to 5. It means this is not equal to 0. Got? This charge is at a position where the field is larger. It means this charge will experience a more repulsive force, but the field is along this way, the force will be this direction. This is negative charge, the force will be opposite to the direction of the field, as its property says. So the net force on the entire system becomes difference of the two forces. Suppose you have a rod and at its ends two balls are attached, that is simply dipole. But what happens to those two balls? Those two balls are being pulled by different forces, but in the same direction of, or their line of action of the two forces are equal. So they will be moving in a particular direction, obviously, because that direction will be the resultant of the two forces. So this dipole will experience a net force, right? This is called a net force, which will be non-zero, and the direction of the force will be along the electric field. Again, see carefully, the dipole moment is placed along the increasing field. This is the direction of the field E, and this is the direction of the dipole moment P. So the net force will also be along the electric field. That's it, the outcome. So there are some MCQs of last. Now next case is, what happens if the field is increasing this way as in earlier cases, but the dipole is reversed. So this is electric field, this is electric field increasing this way, right? And the dipole is placed in anti-parallel position, that is, this will be positive and this will be negative. So the dipole moment is P vector, that will be along this direction. P vector will be opposite to the electric field, that is anti-parallel condition. And that was parallel condition. Now what happens? Again the field value will be same as we described here, 1 Newton, 2 Newton per Coulomb, 3 Newton and so on. But now imagine what will be the net force. This charge will be repelled, okay? So this charge will be repelled or will be forced to move along the direction of the field. So this is F1. But this force, again this is 10 Newton. The direction is this way. Now here the charge is negative and electric field is having larger value. The electric field if larger, suppose, then what will be the force? Obviously more than this 10 Newton. Again consider this is 15 Newton. But this 15 Newton will be opposite to the direction of the field. Right? It means this field, this is my F2 and this is denoted by a longer arrow, this is a smaller arrow. So this force F2 will be now more than F1. So what will be the result? The net force on this entire system will be towards this way. This will be the net force. F is equal to again F2 minus F1, and this will be again equal to plus or minus whichever direction you are comfortable with, but this is obviously non-zero, and this force will be opposite to the applied electric field, right? Because this is low force, this is high force dominates the system. If it is free, it will move this way. That is, if suppose in the background we have a source of positive charge, so that it is producing electric field, the system will try to come towards the source. However, the arrangement may be complicated so that the field is becoming non-uniform. That's not a part of business for this particular topic, so don't go for this. The final answer is that when the dipole is placed parallel to the increasing non-uniform field, a force acts on this along the field. When it is placed anti-parallel to that of the increasing field, a net force acts on it but in opposite direction, right? So this is electric field. This is dipole moment. Dipole moment is anti-parallel, so a net force will act on this in the direction opposite to that of the applied electric field. That's it. Okay, so this is the conditions.